Hello students, welcome to another session of online class. Today we are discussing about another topic regarding the potential field. After potential field we are discussing about potential gradient. Okay, so what we have learnt in the last class, we have discussed about V is equal to minus integral VAB is equal to minus integral E dot dl from the position B to A, right? So B is the initial and A is the final position. So if you bring a charge from B to A, unit positive charge from B to A, what is the work done? That is called the potential difference. That this is what we have learned. And we have also seen VAB is the difference between the absolute potential at A minus the absolute potential at B, right? So VA is the absolute potential at A, VB is the absolute potential at B. Now absolute potential is nothing but bringing unit positive charge from infinity to that point. Okay, so that is called the reference. Infinity is the reference, so that is called the absolute potential. So reference can be taken anyway, since VAB is known and we don't know the absolute potential of A and B. We can assume some of them as one of the terminal as 0. For example, if you consider VB is equal to 0, then VA becomes VAB. So that is what we have discussed for different cases of batteries and potentials. So this is what we have learned. Also we have discussed about the potential field, the potential felt experienced in a region, right? That is also we have discussed. Today we are moving to a new topic called potential gradient. Okay, so before moving into potential gradient, the different methods of finding E we know, right? One from the charge, another from the charge distribution, and another also we have another method using the flux density. Okay, but all these have a vector quantity and it uses the charge or something which is not measurable as easily. But if we have anything which can calculate, electric field intensity from a measurable quantity such as voltage, because the voltage is the measurable quantity which we do normally in our labs, right? So if we have any option to do this, then it will be easier. And we have a relation V is equal to minus integral E dot dl, right? So this can be written as delta V. We can take delta V, a small volume change. For example, consider a field like this. There is electric field lines moving like this, okay, and electric field direction is this one. Okay, now if I am considering a small element in length element delta L, which makes an angle theta with the E. Okay, now what will be the value of this one delta V? That is nothing but the potential difference between these two terminals will be E dot delta L, right? Or E delta L cos theta. E delta L cos theta. So how we get E? E cos theta, mod E mod delta L cos theta. So what is mod E cos theta then? That will be delta V by delta L. Now if we apply the limit, make limit delta L tends to 0, then what happens? Delta V divided by delta L is equal to E cos theta, and the LHS part of this is nothing but dV by dl, right? The differential of dV along the direction of dl is nothing but E cos theta, okay, mod E cos theta. So when it becomes exactly mod E, at a particular condition, this will become mod E only. So that, or we can say in other words, what is the value of dV by dl maximum? dVl by dl max will available when E is maximum or cos theta is maximum, but we don't know, right? So only possibility is cos theta is maximum. So when cos theta is maximum, when theta is equal to 90 degree, so we can say that dV by dl is maximum when E theta is equal to 90 degree. That is, the electric field and the delta L, the potential difference which you are finding, should be perpendicular to each other. At this point, E, magnitude of E is dV by dl, right? So dV by dl is in this direction here, and E is in this direction, so they are perpendicular to each other. So what we can write about vector E? What is the value of vector E then? That will be dV by dl, that is the magnitude, and the direction is perpendicular to the direction of E, so it should be an cap, right? So that is E is equal to dV by dl an cap. So this quantity which is perpendicular and is having some scalar in it, so this should be, so you have a minus sign here which I left here, so it will be minus minus minus, or E is equal to minus dV by dl, so E is equal to minus dV by dl an cap. So from this we came to know electric field intensity is the negative differential of voltage or potential, right? And it is perpendicular to the direction of this one. So this quantity, the negative differential with a direction, is nothing but called gradient. Okay, dV by dl is gradient of V. So this quantity, it should be negative d by dl, that is the derivative with respect to length, and it should have a direction. So such quantity is called a gradient. As we defined a del operator, here also divergence there in the previous classes, here also we have something called a gradient. Okay, so E is nothing but minus gradient of V. Now what is gradient we will find. Now what is dV? dV is V is a function of x comma y comma z, right? So if you want to find the value of dV, I should differentiate with respect to x, with respect to y, with respect to z also. So it will be dou by dou x of V into dx plus dou by dou y. With respect to y I have to differentiate, then I have to multiply with the dy, and dou by dou z of V with the value dz. Right, so dV is equal to dou V by dou x dx plus dou V by dou y dy and dou V by dou z dz. So this is what we have dV. Now also we have discussed that dV is equal to E dot dl, right? If you integrate, we will get V, so minus E dot dl. So from this one it will be E x ax cap, minus is there, plus Ey ay cap plus Ez az cap dot dx ax cap plus dy ay cap plus dz az cap. So if you multiply, it will be minus Ex dx dot product will be Ey dy and Ez dz, correct? So compare these two equations, let it be 1, this is 2. So here you have dx, here you have dx, so this should be same, right? Because the LHS is same. So dou V by dou y should be Ey and dou V by dou z should be Ez, but there is a minus sign. So from this I can write Ex is equal to minus dou V by dou x and Ey is equal to minus dou V by dou Y, and Ez is equal to minus dou V by dou Z, and totally electric field intensity E is equal to minus dou V by dou X, that is Ex Ax cap, plus dou V minus is common, so dou V by dou Y Ay cap, plus dou V by dou Z Az cap, correct? So if I take dou by dou X Ax cap outside, dou by dou X Ax cap plus dou by dou Y Ay cap plus dou by dou Z Az cap of, so this acts as an operator on a variable parameter V. Actually I should not take V outside, actually I am not taking V outside, but this is an operation on V, this is another operation on V, this is another operation on V. Remember, this is not taking outside as we do in other calculations, it is not taking outside. This one operator, same operator, another operator, and doing it together, adding them together, I am writing it separately, that's what I have done. So minus is there. So this is what we have learnt in the last class, is called an operator called del. So del of V. So this is the very important expression. E is minus del V, and we have seen E is minus gradient of V. So from this I can say gradient operation, gradient of V is nothing but del of V. Okay, so we have different coordinate systems, right? Cylindrical is there, Cartesian is there, and spherical is there. So generalizing the gradient operation, so gradient of V or del of V is nothing but 1 by h1 dou V by dou U plus 1 by h2 dou V by dou V plus 1 by h3, this is small v, dou V by dou W, right? So can you tell me, different coordinate systems, what will be the value? In Cartesian, del V is nothing but del of V, gradient of V is nothing but dou V by dou X plus dou Ax cap. So something is missing here. Au cap is there, Av cap is there, Aw cap is there. Okay. So del operator is an vector operator, V is a scalar. So if you do gradient of V, you will get a vector as the result, right? So in Cartesian coordinate system, del of V will be dou V by dou X Ax cap, dou V by dou Y Ay cap, and dou V by dou Z Az cap. Okay. In cylindrical, how it will be? Del of V, gradient of V will be how much? Dou V by dou rho 1 by h1. H1 is 1, right? So you have this system UVW. So and h1, h2, h3. So UVW in Cartesian it is x, y, z, and 1, 1, 1. And it's cylindrical, you have rho y, z, and this is 1 rho 1. And spherical, you have r, theta, and phi, and this is 1 r sin theta. So 1 by h1, 1 by 1 dou v by dou rho, a rho cap, plus 1 by h2, that is 1 by rho dou v by dou phi, a phi cap, plus 1 by 1 again, so 1 dou v by dou z Az cap. And in spherical we have del v is equal to dou 1 by h1, that is 1 dou v by dou r AR cap plus 1 by H2, that is 1 by R, dou V by dou R dou V by dou theta A theta cap plus 1 by H3, that is 1 by R sin theta, dou V by dou phi A phi cap. Okay, so this is how we are calculating the gradient in different coordinate systems. Now we will discuss a problem here. So given the potential field V is equal to 2x square y minus 5z, so this is a scalar, so there is no direction components, and a point P minus 4 3 6 at a point P 4 3 6 at a point P. Calculate the numerical values of question A, potential, B, electric field intensity, C, direction of E, and D, that is flux density, and one more, you can also find the value of rho V, that is the volume charge density. So the first question A, so A, what we have to calculate is the V at P, that is at minus 4 3 6. So what is the expression for V? V is equal to 2x square y minus 5z. So V is 2x square y minus 5z. So 2 into x square is 4 square, that is 16, y is 3, minus 5z, 5 into 6, so that will be 32 into 3, so 96 minus 30, so that will be 66 volts at P minus 4 3 6. So this is how you have to calculate the value of V. The question B is you have to calculate the value of E. So just now we have derived the expression E is equal to minus del of V. So which coordinate system is this one? This is the Cartesian coordinate system. So del of V is nothing but dou V by dou x Ax cap plus dou V by dou y Ay cap plus dou V by dou z Az cap. So that will be dou V by dou x. So with respect to x, if you differentiate, that will be minus, with respect to x, 2x square y, so 2y is constant, for 2x square it will be 2x, so 4xy x cap plus dou V by dou y. So with respect to y, this part will become 0 with respect to x, so here it will be 2x square, and with respect to z it will be minus 5z, so this term will cancel, with respect to z this will become 0, and only here you have minus 5. So you have to get the expression for E and the value of E at P. Substitute the value of x and y. X is minus 4, y is 3, so you will get minus 4 into minus 4, that will be 16, 16 into 3 48, so minus of minus, plus 48 Ax cap plus 2x square. So x is 4 square, minus 4 square is 16 into 32, so that will become minus 32, so this minus comes here, so minus 32 Ay cap, and minus 5, minus of minus, plus 5 Az cap, nothing is there to substitute. So you got the value of Ep. Now what is the magnitude of Ep? If you want the direction, you also should know the magnitude, right? So mod Ep is nothing but square root of all those values, 48 square plus 32 square plus 5 square, so 48 square plus 32 square plus 5 square. So if you find the value, it will be 57.9 volt per meter, and the unit of electric field intensity is volt per meter. Okay, now direction of E. Direction of E is nothing but unit vector along the direction of EP. So that will be E vector EP divided by mod EP. So that will be 48AX minus 32AY plus 5AZ divided by 57.9 is the magnitude. So dividing, you will get 0.829 AX cap minus 0.553 AY cap plus 0.086 AZ cap. Okay, so this is the direction of E. Okay. Now next what you have to do is you have to calculate the value of D. So D is flux density. So how to calculate the flux density? D is equal to epsilon times E. So substituting epsilon, 8.854 into 10 raised to minus 12. So if you substitute that value here, multiply with 48 AX minus 32 AY. So epsilon 0 into 48 AX cap minus 32 AY cap plus 5 AZ cap will give you 35 point minus 35.4x 4 okay. D, we want the value of D not at P. So if you want D, you have to substitute in this expression. So here minus 4xy ax cap plus 2x square plus, so this is the expression, right? So I will erase this one now. So the question is asked about D intensity D, then we have to substitute, not now. So we have E is equal to minus 4xy ax cap minus 4xy ax cap plus minus 2x square minus 2x square ay cap plus 5 az cap, right? So plus 5 az cap. So epsilon times this one, if you multiply, you will get minus 35.4 x y ax cap plus 17.71 ay cap x square ay cap plus 44.3 az cap pico coulomb per meter square. Okay, so that comes here, pico 10 raised to minus. So this is the expression for D. Now the last question is to find the value of rho v. So we have to apply the Maxwell's first equation. What is the Maxwell's first equation? Rho v is equal to del dot D, which is nothing but dou d by dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Okay, see the difference here. We have to find the differential with respect to x, y, z components separately as x derivative, y derivative and z derivative, whereas in gradient the same function is used for all of them. So the value what you will get here with respect to x, it will be minus 35.4 y, right? Here it will be x square with respect to y will be 0, and with respect to this also it will be 0. Now we have to find the value of rho v at p, because rho v is the expression of minus 35.4 y. Now rho v at p, if you want, rho v at p will be minus 35 point y, and you have to substitute the value of y. So what is the value of y? Y is 3. So that will be minus 35.4 into 3. That will be minus 106.2 picocoulomb per meter cube. This is the charge density, charge per unit volume. Okay, so that's all for today's class. Thank you.